All right. Hey, everybody. Welcome back. Hopefully everybody had a nice holiday off. We went ahead and just skipped the July meetup this year. So anyway, hopefully, yeah, everybody is staying healthy and safe, and welcome back. So yeah, I do this every time. I'm got the wrong window focused here, and see, there we go. All right. So welcome again from the steering committee. My name's Paul Baylog. I'll be hosting here, and then I'm joined here with Sabri Blackman and Brandon Hunter. He's out in the audience there, and then Siju John. He's not going to be here with us today, but he'll be here with us in spirit, I'm sure. So he had some other stuff going on today. So anyway, welcome. We are your steering committee, and let's go ahead and go through some of the stuff that's coming up. I just want to also thank our sponsors. We have GoBridge. It's covering all the meetup fees. They've been, I guess we've been associated with them for quite a while now, well over a year now. And then recently now, the last probably, 3 sessions, we've been kind of under the CNCF umbrella as well. The Crowdcast fees for hosting this. So anyway, I'd like to just make sure everybody knows that, with both of these groups, they both have their individual codes of conduct, and then as such, we're kind of covered under those, and just basically, be good to one another, be excellent to each other, as Bill and Ted used to say. So, okay. All right. So here's our section, our normal section. We just like to discuss any kind of new stuff that might be out, anything somebody's, stuck on or whatever. It's a little bit difficult in this virtual situation, but we'll go through here. GopherCon is coming up. Now it's going to be a virtual event that's, as everything is. And then that'll be November 9th through the 13th. And then it'll be $100 tickets. They do have additional ticket options as well, which will buy you a discount for future GopherCons as well. So that's something I'll probably be checking out. That should be a good one. Also, CNCF will have their KubeCon North America. Possibly you might have attended the ones from EU last week. I know I did. I woke up at about, 5:30 a.m. local to attend these things, but I had coffee, so it ended up being good. So anyway, ticket prices are TBD at the moment, but they do have diversity scholarships. And I forgot to mention, I'm sure that for GopherCon, there's probably diversity scholarships as well. So anyway, but those are some of the things coming up. I don't know if anybody has any kind of questions. Oh, Brandon, here's 10 Pauls. That's never a good thing. No echoes from anybody else. Okay, good deal. All right, so Brandon, it's just you. All right, so seeing no questions coming up, we'll go ahead and proceed. So today we get the fun of having a lightning talk by our own Sabri. So, I'm going to hand it over to you, Sabri.
Cool. So I could not get screen share to work on Linux, so I'm on Windows.
Oh, wait. Now I'm hearing like no audio from you, or very low.
That's probably better.
Oh, there you go.
Okay.
Perfect.
Dog mic, I'm sorry. No, I could not get screen sharing to work on Linux, so I am on Windows, which means some of these will be screenshots, but that should be okay. So let me see if I can...
We won't hold it against you.
Yeah.
And by the way, it's Miller Lights tonight, just in case.
There are too many video sources.
Okay, let me close this one then.
Okay.
Now you should be able to.
All right. Let me move this window over here.
We run a tight ship here, people.
You know. Okay. Present, and we should be good. Cool. It looks like that works. Everyone see my slide?
Yep.
Cool. All right. So I thought it would be a good opportunity for especially a lot of the people who are new to Go to do a very, very high level overview of some of the available IDE options. Go is pretty popular, so there's quite a few choices out there, but there's some nuances and some differences in between the current choices that make them better or worse for certain people and certain users. And so effectively going into that. So current state of Go development environments. By the way, if I've missed something or missed your favorite tool or anything like that, or maybe a feature, please let me know in the chat and I will update this for the future. Okay, so hopefully this works. Some of you might be saying, but you don't need an IDE, and you know that's true. But a lot of people find them essential for their jobs, for working on larger projects, and it's also true that a lot of folks who are coming into Go, especially, don't have command line experience, and you know. For those folks, navigating and learning an IDE is often a much easier lift than trying to learn PowerShell or Bash from scratch. And there are other sorts of reasons there too, including debugger support that even folks who are familiar with Bash and PowerShell and things like that may find that an IDE is a lot easier to get started with. Trying to keep this under 5 minutes. The first and most popular is probably Visual Studio Code. I think there's actually data now suggesting that Visual Studio Code is the most popular way for Go developers to code now, as far as IDE is concerned. And yeah, because New Microsoft loves open source, they've been putting a lot of resources and sort of marketing behind Visual Studio Code, so don't let Visual Studio throw you off. It is free, it's open source, and has a lot of extensions and tools. Angry, yes. So the other part of that is that Visual Studio Code, the Go plugin, is now an official part of the Go project. And so there was an announcement earlier this year, June, that the plugin is now being supported by the Go team at Google. It's a very interesting sort of cross-company collaboration. But so far, it seems to be working quite well. See, I'm sure that's over 3.5 million installs at this point. It's well vetted, and the partnership is. I'm hopeful. Too long didn't read version for Visual Studio Code Go. A lot of it isn't necessarily the plugin itself. It's Visual Studio Code, which is, it has a huge plugin library, and you know, basically there's a plugin for every file extension and code and anything that supports infrastructure or programming. There's probably a plugin for it. Again, mentioned the official Go plugin support, which is super, super cool. And it also supports Delve debugging. Delve is, you know, probably the most mature Go specific debugger out there. It is Go routine aware, which is super, super helpful. And it does not use GLS. This is a bit more insider for folks who have used Go before, but it's the Go language server, which is sort of a, if you're coming from other languages like Rust or Haskell, you may be familiar with like this concept of a language server. which presents like an ability to query things for autocomplete, and it sort of runs in the background and analyzes your code as you're working on it. But this can be enabled. I haven't used it personally, but I've heard, for the most part, good things. Cool. And then there is a Vim mode supported. So if you are familiar with Vim, you can use Vim tooling within Visual Studio Code, which sort of goes into Go Vim. I'll show you screenshots of what all these tools look like. And let's see if I can do that without causing too many issues. Here we go. So I found this really good article here. This is, if you're familiar with Visual Studio Code, that's probably really, really tiny. Oops. It does support syntax highlighting and things like that, but it also supports tests and benchmarks built in, and of course the debugger. If you have more questions about that, let me know. And then this works a lot better on Linux. Oops. All right. Go Vim. Go language support for Vim. Again, we kind of went over Go language server. There is now support for that in Vim. Go Vim is one of the most beloved Vim plugins, which is pretty nice. If you've never used Vim before, it is a terminal-based editor, and which is great for people who aren't necessarily running window managers because efficiency or because they don't like them for some reason. Too long didn't reversion assumes a good foundation of Vim. You really do have to understand Vim in order to use it. It does work well with tiling window managers because of saying line wrapping mostly. But it does have a very, very, very strong community. And so because it is Vim, you get all the nice Vim scripting and shortcuts. It will respect all of your defaults in any custom configuration that you have. And autocomplete and refactoring also work really well. This is something that I've missed with other Vim plugins. Before, there was no good refactoring. But there's pretty good refactoring support now with Go Vim. And I will show you that. This is actually an example of autocomplete. And so this is Go Vim on Windows, which I thought was really, really cool. And, it's very, very bash heavy.
Coming up on that time, Paul.
All righty. It is that time.
Oh, it is. So hopefully everybody's back and a little relaxed and stretched, and they got their Miller Lite because it's Miller Lite time. I'm a whiskey drinker by trade. Irish whiskey. Who knew? Kennedy. But I drank a little coffee here to make sure that we're good. No, plus it's Wednesday. I try to start my whiskey drinking on Thursday. So all that being said, thank you for everybody who's sticking around. Before we get going and I share my screen and we go through this, I just want to say a few things. One, this talk that I'm going to give is really designed around the idea that I want to share with as many people as possible what the draft syntax is looking like for generics. All right. So if you have really been heavily experimenting and reading the draft document and going through it, this talk might be a little boring for you because you probably know everything I'm about to share with you. But I know how many people are busy working every day and just don't really have time to go through this stuff. And it is critically important that everybody's voice is heard and opinions are heard about the syntax, because once this gets locked in, I mean, there's really no kind of going back. Now, I also want to say a few more things before we start. I'm going to need about an hour and 5 minutes to get through the syntax for you. That sounds like a long time. It's going to go by really quickly, okay? And then I'd like to give us about 20 minutes to a half an hour to be able to talk about it and hear people's thoughts and opinions. So we're probably looking at finishing this at around 8 o'clock. So whatever loved ones you have to say, I won't be around till 8, now's a good time to do it. While I'm giving the talk, I really, at least on most platforms, and I'm not sure about this one again, but I normally can't see anybody, I can't hear anybody, I can't look at the chat, and I'm used to just talking into space. I have 5 kids. I've been practicing this for 20 years. So that being said, I'm going to give this talk, okay, pretty much non-interrupted from beginning to end. And then I'm going to save all questions at the end. Now, I do expect everybody to be chatting away and having a conversation as I go through this. I don't want to finish this talk and see nothing happening in the chat after that. I won't be able to go back and through and read that chat, but I really want you to be interacting amongst yourselves and talking about the things that I'm showing you. Now, I'm going to be sharing with you the syntax. This is all that we're working on. And it's critically important you understand that this has not been implemented yet in the compiler. It's not. All we have is a tool called Go2Go, which is a transpiler. It will take the new syntax, transpile it into working Go syntax so it can be built and then it can be run. All right. So just remember that we don't really have an implementation yet. And that even means that the draft document that we're going to be exploring hasn't even been 100% implemented, which really wouldn't make sense, right? Because we really want to get to the point where we're building the compiler out, not a tool that we're going to be throwing away. All right. But we're going to do that. Rebecca has thrown another document in the mix, which is a very academic technical document on this featherweight Go idea, which definitely had influence over what you're going to see. Okay, and I appreciate that, Rebecca. I did add 3 links into the chat. I've added them a couple of times. Maybe I'll do it again here. The first link is to the GitHub repo that I'm going to be working against. Okay, well, at least that's where all my current training material is for generics. So I'm going to bring that up very soon. The next one is a link to the draft document, okay? Don't feel like you had to read that. My whole point of this talk is so you don't have to read that. And then there's a Google survey that actually is coming from the language team. And that gives you an opportunity to directly talk to Robert and Ian and everybody that's working on it. And you get to do that anonymously too. So you can say whatever you want. Nobody's going to know who you are, okay? And I think that's important because I don't know if you're like me, but I really get scared talking on the mailing list, and I get scared adding issues into the GitHub repo. I just don't like the large debates that go on. It's just not part of my character, right? So If you're like that and you just don't feel comfortable getting into the public debate about things, that's your opportunity to kind of have a private conversation in a sense, or at least get your thoughts over to language team. So please leverage that survey. I think it's really nice that it's there. All right, so we've talked about the questions at the end. Also, if there are audio issues, please mention something in the chat, and Paul, if it's happening to a bunch of you, will interrupt me and let me know. If you're having visual issues, the font is not big enough, things are lagging, I don't know. So if you don't start to tell Paul, Paul can't tell me, and then we can't get it corrected. I really want you to be able to focus and enjoy the code. Also, this talk assumes at some level that you're Go developers, right? So if you're brand new to Go, I've tried to keep the examples fairly, I think, reasonable, even for somebody that's only been working in Go for a couple of weeks. The examples will get a little bit more complex over time. So just stay with me as we go, okay? Because we're not gonna really teaching Go. We're really kind of showing the syntax, why we have it, why we need it, and how it's playing out right now. I think with all that being said, we can go ahead and share my screen here. So how do I share screen? Oh, there it is up there, share screen. Brilliant. I'll share the entire screen. Okay, Paul, let me know if you see this screen right now. Again, I'm blind.
I do. Oh, here we go. It's there. Let me focus it so it's larger. There we go.
Okay, so everybody can see that fairly clearly. Before I talk, is that large enough? I'm going to get into this code obviously here, but is that large enough, or you think I need to go larger like this?
For my old eyes, they seem to be.
This is better. Okay. And then last thing right here, at that point, I'll go a little bit larger there. So all that looks good. Excellent. Yep. Great. Let's kick this thing off. It is now 6:47 your time, marking 47 minutes after the hour. I'm going to keep my eye on that clock. When it's 50 minutes after the next hour, that's when this part of the talk is going to end. I'll keep my eye on that, I promise you. Okay, I'm showing you very quickly the repo for the generics examples. You can see here there are 12. There is no way I could get through 12 of these in an hour. I'm not even going to try. I don't even need to. All right, we're just going to get through the first 5 of these, and that will give us, I would say, about 85%, if not more, of the proposed draft syntax, at least the most critical parts of it that we really have to, as a community, kind of nail down. The rest of this code, 6 through 12, that's for you to explore later if you want to. And it just, again, it gets a little more complicated, and it shows you maybe some more practical applications of generics, like using channels and other container types and slice constraints and things like that. We're not going to get into it. My goal is to get through these five in the next hour, 50 after the next hour. Now, if you go into the README, there is a link right here that will take you also to, and I didn't mean to hit it like that, into the draft design document. I gave you that link already in the chat. This link here sends you to a Go transpiling playground. I won't be using the playground tonight. I'll be running things on my local machine. However, if you end up with questions that are code related, and you can put it into a playground link, then you can share that with me. That's brilliant. You might even come up with some really nice examples that we could use to teach. So leverage this Go playground and even share that amongst yourselves while you're chatting about all the stuff I'm showing you. Okay, brilliant. Now, I'm not going to read this, but this is your high-level overview. This is what is currently slated to be in the first release of generics. You heard me right, first release. Once this gets released, I would expect releases moving forward from that point. When, Bill, are we going to have the first release? Well, right now, I think that the earliest you could ever see any form of an actual release in the compiler of this would be a year from now. That would be August of 21. That would be version 117 of Go. I don't expect that, though. I think we're going to see something in 118, which would be the February release of 22. Remember, we're just focusing on syntax right now. There's bunch of things that still have to be considered and implemented, even around the actual implementation. So these dates are not coming from anybody other than myself. And let me reiterate, I don't work at Google. I don't work on the Go team. I'm just a regular developer like you. But I think this is going to be probably, we're looking more at a 118 February 22 release. I'm gonna stick to that. I could be wrong. Could be one release earlier, one release later. I think that makes sense. Anyway, this is what we're currently looking at, and this is really what I'm going to be showing you over the next hour. These things, I'm not going to read it. You can look at it. You can see what's there. Now, the document also has a high-level overview of the emissions, things that are currently not slated for a first release. Now, that doesn't mean that somebody might not make the most perfect argument that this has to be in a first release, and therefore it ends up being in. But if you're looking at hoping to have this stuff at least day one, I wouldn't hold your breath. But maybe day 2, day 3, as it is needed. These are things that might come in to the generics part of the language. So you got that, you've seen it. Now, there are blog posts out there that can give you more. I've got 2. I'm working on the 3rd one now, and these are literally based on the code examples that I'm going to be sharing with you. And then I'm also running the Go tooling locally. So these are instructions on how to do that. And before I came into the talk tonight, I did update my local source code for Go. And if you see me do a Go version here, you can see it doesn't say 115. It says this is a release of code from today at 4:50 p.m. So there we are. I'm running this version of Go, which has the Go tooling. And I'll do everything here on my machine. But you have a playground as well. And you've got access to this code right here on the repo. So you can have a lot of fun following along and playing with it. And I really hope I hope everybody here enjoys just having that conversation about what I'm going to show. Okay, it's 52 after the hour. I'm 2 minutes in already, so let's not waste any more time. All right, let's get into this first example. And what I really want to do with this first example is start to show you not just the syntax, but even why we need a new syntax. And I think the idea of understanding why we need new syntax here helps to understand at least some of the syntax choices that we do have. And one way that helped me kind of progress through my understanding was to build different versions of the same function until we got to a generics version. And that's what I'm going to do right now. So let's start here on line 13 in that very first example. And you see a function named print numbers. Now, print numbers isn't doing anything spectacular, right? It's accepting a slice of integers. It's accepting this collection of integers via that Go's main data structure, a slice. And in 5 lines of code, I print a label. We do a linear traversal across this collection using our for range mechanics. There we are. We use our print function to display each individual index. And then I do a carriage return line feed at the end. 5 lines of code. That's what it's taking here to write print numbers, to print all of the numbers in any given slice or collection of integers that we get. And one of the things I want to make clear, and I'm going to be expressing my thoughts and opinions as we go, and at the end of this, you don't have to agree with everything, but you can tell me where you do and don't at the end. I'm going to make an argument here that I think all Go developers, and even non-Go developers at some level, but even if you're only a Go developer for a couple of weeks, I think you could read and comprehend this code fairly quickly, right? Because we're really able to use our language mechanics and our language syntax here to do that linear traversal, and then this print package to print everything out. I'm just going to make the argument that I think a very large number of developers can comprehend and read that code. Now, I love the idea of reading comprehension, right? Like, one of the big philosophies I have is make things easy to understand, not easy to do, because that helps always in the long term. So now on line 21, if I want to do the same sort of operation, but it's not going to be a slice of int, it's going to be a slice of strings, I go ahead and I write another function, and I change really the only thing I need to change, which is the type information and the variables. So the code is, again, comprehensive not comprehensive, right? More comprehensible and readable. But it's the same 5 lines of code. You can see that here and here with just some identifier names and type information being different. And now if I wanted to do this with floating point numbers, yeah, I've got to copy, paste, and edit. And so we see this, and I love this code. Even if I'm copying and pasting it, maybe I kind of like it because each version of this function has that easier to comprehend and read, kind of aspect to it. And we really don't want to lose that. But let's do a thought experiment here, just to kind of consider where we can take this. Because you might be saying, well, Bill, I don't want 20 versions of this function for the 20 different types that I have to deal with. So then the question is, well, can we consolidate this functionality into a single function? And the answer is we can do a consolidation. Here on line 35, I've got a function named print assert. And the idea is that this one function can print the collection, at least right now, for int and string, to consolidate those 2 functions into one. Now, the way to make this work is the use of that empty interface, because the empty interface allows us to pass any sort of data in. Remember that you have 2 choices when passing data into a function. You can pass that data based on what it is, using a concrete type, or you can pass the data based on what it can do. That's our polymorphism, right? What it can do based on an interface type. So I'm using an interface type here, except this is the empty interface, which says that the data doesn't have to do anything. And because of that, we can pass any data we want. So now that we can pass any sort of data we want into this single function, we have another problem. We don't really know what the data is. The empty interface tells us nothing. So Go gives us this mechanic on line 37, which is a type assertion. And in fact, if we perform a type assertion on a switch, we can do a generic type assertion right there. And then what we're basically telling the compiler is, based on the concrete value that is stored inside of V, if that type is a slice of int, execute this code. If it's a slice of string, execute this code. And even though we're going to have this consolidation, we do get to at least use variable names that are reasonable for the different type of data that we're working with. But remember, this is just a consolidation for those 2 functions that we have. I mean, this isn't a generic function. We might start thinking about that because I can pass anything I want in. But if I pass in a slice of float, I'm not going to see any floating point numbers show up on my screen. So this really isn't a generic function. It's more of a consolidation of the functions that we had, leveraging type assertions to know which code we should execute here at runtime. So then the question gets interesting. The question becomes, well, Bill, can I even write a generic function today in Go? So not only can I print these ints and strings, but the floats without creating or having to write any more code. And the funny thing is we can. I mean, we really can write a generic version of this print in Go today in version 1.15. And here it is right there on line 56, my print reflect function. Now what this function is doing is leveraging the reflect package that is part of the standard library. And trust me, I love the reflect package. I think it's an incredibly powerful package. I love it for data validation. I love it for marshalling and unmarshalling. And this package isn't going anywhere. It's too important. But it is going to allow us to write a generic version of print for a slice of any type. Now here we are again on line 56 using the empty interface to accept a value of any type. And once again, we need to know what we actually are receiving in the function call. Now, unfortunately, if we're going to use the reflect package, we kind of have to walk away from our language mechanics, don't we? We cannot use our base language mechanics and syntax anymore. We have to work with an API. And so you see on line 58, we use that value of function call with the interface to get a reflect value that lets us inspect the concrete data stored inside of V. And we can do something like this on line 59 and validate that we have a slice. And if we don't, then we just return, which is a bummer because now I'm calling print and I'm not able to see anything, which would technically never happen with our concrete versions. So maybe the semantics are a little different here, but I can do that check. Now, I can't use my language mechanics, right? We talked about that, but I can use at least this increment. In other words, I can't use my for range here, right? But I can increment my I, and then there's a method named index that will let me perform that linear traversal across I. And then this interface function here will give me access to that data in there. And then I get to leverage print to display the value regardless of its type. In fact, up to this point, I haven't mentioned this. I mean, print is a generic function too, isn't it? It can produce an output for a value of any type. How does print do that? The same way we're doing it here, it uses reflect. And so even in the other examples, I'm leveraging at some level reflect, our generic print function, to be able to display values of whatever type I pass it. And I'm absolutely leveraging here on line 63. But we did have a couple of things here, right? The original concrete versions of our functions were 5 lines long. This function here is 8 lines long, and I can't make the same argument that Go developers of all levels can quickly read and comprehend this code. This requires you to study at some level a little bit of the reflect package. But it is a generic version, and it will allow us to display values of a slice of any given type. So there we are. But the question then becomes, at least the question for me, is there value in being able to write a generic version of print that lets us use our traditional language syntax and mechanics like we used here in the functions on line 13 and 21? Because if we could do that and not have to use the reflect package here, then we could get back to code that more developers can read and comprehend. And at least at the end of the day, that for me is one of my highest priorities. Can the average developer on my team read and comprehend the code that I'm writing? And if the answer is not, I have some teaching to do. If the answer is yes, that's brilliant. And so the ability to use this code in a generic way, I think would add a lot of value to the language because we can avoid some of the complexity and runtime checks that we have to now use with reflect. And now this brings us, at least at this point, our ability to look at how we could write a generic print function in Go's new generic syntax. Now, I'm going to do a couple of things here. The first thing I do is I want you to really focus, try hard, focus on lines 81 through 85. And I want you to focus on that because I want you to see that this function is using the same 5 lines of code that I showed you before. We're back to using our language mechanics and syntax, because this function will execute against a concrete type as if that concrete type is already known. Now, you're seeing the use of the square brackets here, and I want to get rid of them for just a second. You're going to see me doing this throughout the talk, because what I'd like to do is just look at this function even before any syntax, because I want you to understand and appreciate why we need some new syntax. So look at this function here. This function right now is saying that I will accept a slice of type T. Now, I think we could kind of look at this and have a general sense of what I'm really trying to say, right? What I'm really wanting to say to the compiler is, I will accept a slice of some type T to be determined at compile time. Not a T that will be determined before compile time, but be determined at compile time. And if we can determine T at compile time, and T can be any concrete type, then we can write code based on the idea that T is some concrete type, int, string, float, whatever. This is where we get the semantics here. But the idea is we need a way of telling the compiler that T is not a type that you're going to find in any source code file by the time I hit build. In other words, we've got to find a way to tell the compiler that that is not going to happen. What I just did on line 80 is never going to happen. Don't even bother looking for it, because you're not going to find it. And this is why we need the new syntax, because we've got to be able to tell the compiler that T is a generic type that needs to be determined at compile time. And how are we going to do that and maintain backwards compatibility? Well, the current draft says the following. When we're going to want an identifier like this to be a generic type, we're going to attach to the, in this case, the function name, a set of square brackets, and this square brackets will declare the types to be generic. And in this case, we're going to say T. Now, if I wanted this to be called Tom for some reason, I can call it Tom. I can even use lowercase tom. There are no rules and or restrictions on what you name these types. But these are new things, and I'm finding, at least right now when it comes to working with these kind of slices, these collections, having these single letter capital names are helping me at least more with the readability. I do have other examples that I won't share tonight that are using larger names for the type identifiers and single letters. You can see that in that code. And this is something I think at some point we'll have to define guidelines and idioms around. But at least for tonight, you're going to see me using T as a generic type to be determined at compile time. Now, the spec has one more requirement for these generic type identifiers, and that is we have to define a constraint. What constrains T, what a T can and cannot be. This is a requirement that any type identifier also be paired with a constraint. Now, the last two examples I'm going to share with you tonight will focus on constraints. Right now, we don't need a constraint. T can be a type of anything. And that's where the word any comes in. Any is a pre-declared identifier, which is an alias for the empty interface. But we don't really want to see that all day, since most, or maybe many of the times, T really won't have a constraint. So what the language is doing is it's adding this pre-declared identifier, any, as an alias for the empty interface. And right now, it will only be available in this one specific case for generic functions. In other words, even though it's going to be a pre-declared identifier and an alias, the language is not going to let you use any anywhere else in the code where you're using an empty interface right now. So when you see any here, what we're saying is T can be anything. And it satisfies the fact that we have to apply some form of constraint to what T can be. In this case, it can be anything. Brilliant. And this right here is the new syntax. And this right here is the new placement of the syntax, at least for our generic functions. And now we're able to tell the compiler is T is a generic type to be determined at compile time, and it can be anything that the developer wants it to be. Brilliant. And now we're writing code with the idea that T is a concrete type, and we get to use our language mechanics and syntax that more of us can read and comprehend as opposed to an API. Okay, brilliant. So let's see this actually work and run. And so what I've done here is I've constructed a slice of integers and a slice of strings. There it is, 91 and 97. And the real point of this is being able to pass the same input across all these functions that we've written and to be able to really see the same output. So with this main function in place, let's go to our terminal. Let's switch over into the O1 function folder, and you're going to see right here a source code file with the .2 extension, because this is going to need to be transpiled. The Go tooling is looking for the Go2 extension. Now, as I said, I'm going to be running this locally, and when you build and follow those instructions, you'll see a new tool show up here from the Go front end called Go2Go. And then it takes the same sort of other commands like build and run. I'm going to just say run now, and then I'm going to give it the Go2 file. And then what that's going to do is transpile Go2 to a Go file, and then it's going to build and run that for me. And when I hit enter, you see the output for all of those functions being the same. Now, this is cool, right? Because the big play here is if I do want to work with floats, float 64, and I'll just make these some floats right now, no big deal, right? then I could use my two generic functions. The reflect one is generic as well. And then I should be able to see that output. Brilliant. So there it is, right there. My two generic functions, without having to write any more implementation, can go ahead and display that slice of floats. Beautiful. And when you look at the function call here, it looks and feels like any function call you've ever made. Now, a big part of being able to make this function look and feel like any other function is the compiler's ability, in this case, the tooling's ability, to be able to infer what type T is at compile time based on the data that we're passing in. And so you're seeing the compiler implement the ability to infer the type. And it's going to be a really critical part of the final and actual implementation of the compiler. You see, the compiler can see that numbers is a slice of int. We're passing a slice of some type T. T matches to an int. We're good. T matches to a float. T matches to a string. And the compiler can do that. Now, what if we wrote a function in such a way where there's no ability for the compiler to infer the type? Maybe we're defining T, but we're not using it here. We're using it internally. Well, just like this defines a set of parameters for data input, this also defines a set of parameters for type input. In other words, we can pass the type explicitly if we want, and tell the compiler, don't worry about trying to infer T. I'm going to tell you what T is. In this case, T is going to be an int, and then the compiler will make sure that this all matches, right? And so we can explicitly pass the type information in. This code will still work, whether I leverage the ability for the compiler to infer it or not in this case. And this gives us that flexibility to maybe leverage a generic variable, maybe in an implementation detail, where it's not, let's say, part of a data input, and still tell the compiler what it is. But remember, the whole idea of the generic type is that we're defining a type that we're not going to be declaring before we hit build, but that the compiler needs to identify at the time we hit build. And in this particular case, however, we're being explicit. I didn't define a new type necessarily. I'm telling it that it's going to be an int here. Okay, so just in this one example now, what do we know? We know why we need a new syntax, because this type T will not be defined by us. It has to be identified at compile time. We saw how we're using our basic language mechanics and syntax because T is a concrete type. And that gives us back to our language mechanics instead of having to work with an API like reflect. We saw that we do have to apply a constraint to the type list for any type identifier. And this pre-declared identifier any says that T can be anything. And in this particular case, when we're calling these generic functions, if the compiler can infer the type, brilliant, let's do that. So the function calls look like any function call. But with that generic function, we still have the ability, just like you can pass in numbers, we can pass in the type and be explicit. Okay, brilliant. This is our very first example of code and syntax. Now, let's move on. Hope you're enjoying and having a nice, rich conversation there on the chat. Now, this was great. This is nice. It gave us the beginning of the syntax. But let's think about it. I mean, the programs that we write day in and day out, right? They're driven by data. I'm a big believer Go is a data-oriented designed language. If you don't understand the data, you don't understand the problem. Everything is data-driven, which means our ability to declare user-defined types is critical to our ability to solve the problems that we're working on. And in Go, there are two ways of defining a user-defined type. We can define types based on an underlying type. And then we have the ability to use the keyword struct to define a more complex sort of like composite type, right? So we need to kind of look at and study these two ways of defining these types and look at them in the scope of making those types generic. So let's start with our underlying type mechanics. And I'm going to go through the same exact progression as I just did with our function. So if you look at line 16 and on line 25, you see that I'm defining a type named vector int whose underlying type is a slice of int. And on line 25, vector string has an underlying type of a slice of string. And this type lets us build behavior around the underlying type. And so you see on line 18 and on line 27, two methods named last, and last. And if you look closely, the code is really identical. The only difference is this has to work with an integer because the underlying type is an int. This works with a string because the underlying type is a string. But we get to work with the underlying type directly, which does help, as I will show you with usability. But look at what the code is doing. It's validating if the slice is empty or not. And if it's empty, we return the 0 value for an int and or an error. If it's not empty, we return the value at the largest index position in the vector, and then the 0 value for the error, which is nil. And these mechanics that we're doing are identical regardless of the type information. However, the 0 value for a string is an empty string, and this obviously would return a string. And so we see this. And then once again, if I wanted to do this, if I wanted to create a vector of floats, it's a copy, it's a paste, it's an edit. But remember, the return type in the data is just a float, and that really helps with usability. So let's go back to our progression. Is it possible to write a vector right now today that could be more generic? In other words, not bound to a particular type. Well, here we are. Line 41, I can define another type named vector interface whose underlying type ends up being a slice of the empty interface. And remember what I already said, the empty interface is a way of allowing us to store and move data around in a generic way because it doesn't have to exhibit any behavior at all. And if you look at last, right, we're changing out that string, right, in this case for the empty interface. There it is. And we have the same mechanics. Is it empty? Return the 0 value for an interface, which is nil, or return the last value or the value at the highest index. But I think if you sit back, you're going to see that the semantics, right, the behavior of this vector is much different than the behavior of the vector string or int. And that's because when I call last, I'm going to get the concrete data already decoupled inside the empty interface. And I have 0 clue what type of data I'm getting back. For vector int and vector string, I know exactly the type of data I'm getting back. But on this method call, it could be anything. And that's what I mean, that the usability kind of starts to get a little less than we had before, because now we're back to doing what? Type assertions and or reflection to understand what data is actually coming back for this call. There's no guarantee what the data is going to be. And so I think that even though we can do this, and maybe the implementation isn't more complex, the usability is, because this is an unknown. And I think this is where generics can come in, because here is our generic version of a vector. And you're going to see me doing this throughout the talk. I'm going to get rid of the new syntax for a second so we can just kind of study and look at the code in a way right now that our brains are wired for. Because if you look on line 57, what am I trying to do again? I'm trying to tell the compiler I want to define a type named vector whose underlying type is a slice of some type t to be determined at compile time. So we know anytime this identifier for the type, in this case t, needs to be determined at compile time, we have to apply this new syntax. Before we did it at the function name, now we're doing it at the type name. And this again tells the compiler that don't look for t, it's not going to be declared anywhere. The t is a generic type. It could be anything, and it will be determined at compile time. Now, when we look at the implementation of last, this is the cool part right here. I've highlighted right here on the return, because I'm able to return t. I'm now able to return a concrete type whatever that T is. I'm back to the original semantics that I had for vector int and vector string. It's not going to be an unknown situation. We're going to know what T is when we construct this vector because we're going to have to. I love this. We'll know with the concrete types. We're back to the other semantics. Now, this might seem a little foreign to you because we're not just saying vector anymore. Vector by itself isn't enough. Vector now is always going to be represented with the idea that it's a vector of some type T, using our square brackets to do that. I'm going to come back and study that syntax again in a little bit, but I want you to understand what we're saying here is that the receiver is a vector, a value of type vector of some type T, the same T that we're going to be using on the return. The same T associated here with our vector declaration. Now, if you look at the implementation of this last method, you'll see a couple interesting things. On line 61, I still have to check if the vector is empty. And if it is, I want to return the error. But remember, I also want to return the 0 value for T. This is an idiom and a guideline we have in the language that I personally love. I love this idea that we do on the returns, that we usually do our 0 value construction or literals directly on the returns to make it very clear to the caller what they're getting back, especially if there's an error, then expect the 0 value for all other types. If there is no error, expect the 0 value for the error. We have a problem here with 0 value because we don't know what T is. Now, you might say, well, Bill, why can't we do this? Why can't I just say on the return, use our empty literal construction syntax for T? I mean, if T was a user, I could do this. This is how I would have written code if T was a user. So Bill, why don't we just use our empty literal construction? The problem is that we need a universal, we need a syntax where constructing something, some type to its 0 value state works for all types. In other words, this works fine if it's a user, right? But it doesn't work if it's an int. It just doesn't work. This syntax is not legal. And so we're kind of in trouble because, well, not in trouble, but we can't use the syntax because it doesn't necessarily work for all types. Now, this syntax does work for all types. The keyword var will give us 100% of the time, regardless of the type, a 0 value construction in this form. And so this is kind of cool because on line 60, I can declare a variable of my choice. I'm going to call it 0 and say var 0t. And now whether or not this is a user or an int or a string, we get 0 value construction, which now means from a readability perspective, we can use that variable 0 and get back to the exact semantics that we were using before. Now, not everybody's a fan of this variable declaration. I like it. It's not a fan. And there may be other choices before a final release is done. It's not the biggest issue we have right now with syntax. I'll share some of that before the end of the talk. But there is another way to do a 0 value construction for all types. And that's using the built-in function new. So the built-in function new lets us construct a value, whether it's an int, a string, or a user, to a 0 value state. But the problem is that you don't get back a value of that type, you get back a pointer. And so if we want to use the built-in function new, we then also have to dereference the pointer to satisfy T. This is your other option. Now, I've met developers over the last couple of months who do prefer line 62, but I think they're more advanced developers. I think if we're looking to make sure that more developers comprehend what we're doing in code, I personally think that this syntax is a little bit more complicated than this syntax. And so this is kind of where I'm heading. Now, it's quite possible that before this is done, and there's been a little bit of talk on it, it's just right now not our biggest problem. But maybe the language maybe the language can give us 0 for free here. And then we don't have to declare anything. That would be really cool. But right now, that's not where we're at. So those two choices might end up being the final choices in a release. They may do something where they give you something that maybe pre-declared, or they can do a compile time called 0 for that. I don't know. That conversation is not being had, but at least you see this here. And then you understand what we're doing. Okay, brilliant. So there is our vector. Now, back from the usability side, right? What I was really loving about vector int and vector string was we always knew we were getting back an integer and a string on the last calls. So I could immediately do things like this. Is the value negative? Is it a valid string? Right? There's no issues. And remember, I told you that there's some usability issues with vector interface. Look at what I'm doing. I'm intermixing data. So in this particular case, int, string, float. Well, guess what? Happens to be a float at the end of this, but we don't really know that, because when I call last, I get that floating point number, but it is what? It's it's abstracted away from that inside the interface. So here I am again doing type assertions if this particular logic is important, if the last value is an int, a string, or a float. So you see the usability here got a little bit bigger. But let's take a look at our vectors here. Now, let me kind of reduce the noise a little bit so we can kind of see this, right? Remember what I said before. This doesn't work. Here, I'm trying to do a 0 value construction of a vector. But remember, vector in and of itself doesn't mean anything, because we have to tell a compiler what the underlying type is going to be. And so when we're dealing with these 0 value constructions, we're going to have to be explicit with the compiler and tell the compiler what T is going to be. Now, look at the construction syntax, because for me, this is important. Notice the construction syntax here is a vector, square brackets of type int. Let's go back to the receiver. What do you see? You kind of see that same construction syntax, a vector, but of some type T, because T has to still be determined in the implementation of this function. So it's the same sort of syntax coming in here on the construction call. Now, you're also seeing me do this right now on line 110. And you might be saying, Bill, why are we explicitly passing int here when we're initializing the vector with integers and the compiler could infer that? If you're asking that question, you're absolutely right. The draft document does state, well, I don't know if it literally states it, but does support that if we did this, that we wouldn't have to explicitly pass the int in, because the compiler could infer the type. But remember what I said, that right now what we have is a go-to-go transpiler tool. And remember when I said it wasn't fully implemented, because we shouldn't necessarily do that, because what we really want to do is spend more time actually building out the compiler than the tool where we can? Yeah. So the current tooling has not implemented, at least the last time I ran it, the ability to infer the type with this syntax. It doesn't mean that it won't be able to do that in a final implementation. It just can't right now. So you're seeing in this example me having to explicitly state what the type is during construction, because it's just not inferring it yet. It's not implemented. But how beautiful is this? We know we're getting back an int. I can do all of that. We know we're going to be getting back a string. I can do all of this. I don't need type assertions again, right? I don't need type assertions. I can come in here, run the tooling. There it is. It builds. It has output. Here's our vector int. Here's our vector string. And then once again, what do we talk about? We talk about the ability to not have to implement any more code to be able to work with floats, right? We can just do this. We can do this. I can make this variable an f. Right now I know that we've got a float here. I can even check for negative numbers since it's a float. We can make these floats. right in here. There we are. I don't have to implement anything. This will give us the ability to now work with floats. Here we are. There's our float. Boom. Beautiful. I didn't change my message, a negative integer, but you understand. So really, really nice. Cool. Okay. However, this is when we're using that underlying type, right? The reality is that I don't know how many types I've really written in a lot of code over the last 7 years using an underlying type. I'm not saying I haven't. I'm just saying it's not as common as using a struct type. So we need to kind of go and look at struct types as well. Now, when it comes to struct types, what we're really looking at in terms of generics is really the field set, right, for the type. And so I think a good example here is the idea of maybe a container type like a linked list. So let's go back again. I'm going to remove this. We're going to put it back in when we need to. But a linked list will have a node type. Now look at this node type on line 14, right? And really the idea is 15 because I could define this node to just work with integers. But if you've ever implemented a linked list before, you know that maybe 80+%, if not more, of the code is the same, regardless if we use an int, a string, or even a user. And so this is one of the areas in Go where we're really lacking, or where things can start to feel tedious when we're kind of building these types of container types. We want the data to be of some type T to be determined at compile time. And because we want data to be of some type T, what are we back to doing again? That's right. Anytime we're trying to talk about that type being a generic type, then we've got to tell the compiler it's a generic type. And again, T can be anything. Now, our next and previous pointers have to point to nodes. But we already talked about this in the last example, right? You can't just say node because this isn't really a node. It's got to be a node of some type T. You see that construction syntax again, right? And it's got to be of the same type T that we're using to construct this node. And so that's why we see this syntax here. Again, you saw it with the receiver. Now, a list also has to be generic. A list has to, in this case, has a first and last pointer of some type T. And so whatever we define explicitly for the list, that will also be defined for the nodes, and then that node will all apply. Look at the add, just to have a basic implementation of this container type. Look at the receiver, list of some type T. We understand that. And even though I'm using my pointer semantics like we should here with our list, notice that add returns a node of some type T. There again, and accepts a value of that same type T as an argument. Look at the construction syntax here. On line 26, we're constructing a node of some type T to be determined at compile time, whatever the type is that we pass in. You're seeing construction syntax. I'm not being explicit here. We're letting T flow through. The rest of this code, right, other than the assignment of some type T, they better match this T. The rest of this is boilerplate, right? This is the problem. That doesn't matter what T is. That's not going to change. And so you see here with our struct types, we're able to define fields of some type T, and we're able to point to nodes of that same type T, lists of that same type T, methods of that same type T, values of that type T, all to be determined at compile time. Now, we want to see some implementation here. We saw implementation. If you want to see me run this, instead of using an int and a string, here I'm defining a type named user. User will be what we're going to use in terms of the data that this list will store. And on line 53, you see my zero value construction again, where I have to be explicit about the type of data this list is going to store. This list is going to store user values, which then applies to our add methods that accept values of type user, which applies to my data field, which will be of type user. This list is being set to its zero value state, where T is going to be a pointer of type user. So add now accepts pointers of type user. That's my pointer semantic construction of a user, right? Ampersand. And then data will be pointers. And if I build and run example 3, you see the output from print saying values, and then you see the ampersand here showing that really we're storing pointers of that user type. Really nice. Now, what happens if I decide as the developer of this container type that I want to enforce pointer semantics? That for some reason, I don't want the user to be able to store data in a value sort of semantic. I want to always force the pointer semantics, which means I'm forcing pointer semantics on this parameter. What happens? Well, let's take a look at what the compiler tells us. Now, for a second, I'm going to just comment this code out. We'll just focus on line 53 through 56. But look at what the compiler tells us. It's, you cannot use user literal on the call to add. This is line 54 and 56 is the call to add, because that function wants a pointer of type user. Well, that's fair. You saw me do that, right? You saw me say that this has to be a pointer of type user, which then complies with the data field because we've hard-coded a pointer of type user. I'm now having to do pointer semantic construction here to fix it. That works. You might say, well, Bill, that's not really a big deal. Maybe it's not, but the type information really isn't matching from the point of construction to the add method. But look at what this is doing. Now I'm saying T is a pointer of type user. What does the compiler now say? Double in direction. Why does it think that the add is now wanting a pointer to a pointer? Well, let's do the substitution ourselves. We just said that T is a pointer of type user. We just said T is a pointer of type user. You see what happened? We now have a pointer to a pointer in here because the T got substituted that way. Now, what does this mean to you or me? I think what it means, and the pointer that I kind of want to make, is that I like the idea when it's reasonable and practical, and I would argue it probably is reasonable and practical most of the time, to allow the user to dictate the semantic. If the user wants to manage and store values of type user, this allows them to do it. This allows them to use pointer semantics because we're not messing with T. We're accepting T as it is, as defined by the user, in this case explicitly. Now, there may be times where maybe you need to do this. I just want you to be aware that if we start doing that, there could be even inconsistencies in the code, because you might say, well, Bill, you know, yeah, no. So I think I just wanted to show you here some value pointer semantics and how that kind of substitution is taking place. And I think being able to allow the user to define T clearly and then the API follow that can really help with readability and comprehension of the code we're writing. Okay, it is 8:37. I said I would be finished at 50, and that gives me about 13 minutes. That's fine. I think we're in good shape. So I've shown you now essentially how to write a generic function where T can be anything. I've shown you how to write an underlying type where T can be anything, and I've shown you how to write a struct type where that data field can be anything. But we really do need to have a conversation around constraint, because it's probably not going to be very common in more practical and reasonable code that the implementation of the functions are always going to be able to work with any value of type T. I don't think that's going to be reasonable. There are going to be functions you're writing that are going to have some form of constraint. Now, there's really two types of constraints that play here. I'm going to start with the first one, which is behavioral constraint. And this is where values of some type T, we need to have a guarantee that the data for that type T exhibits some sort of method set of behavior. And I want to start with that here in example 4. So look on line 13 and 22. I'm defining types, one called user, one called customer. And I've also added a method named string for both of these types. And the idea of string is to implement functionality bound to a user or a customer specifically that can stringify a user or stringify a customer. And now you can see here that the stringification is a JSON document. It's JSON notation. It could have been anything. But you can see here how we're leveraging methods, name string, return string, to do a stringification of a user and or a customer. Now, look at these functions that I wrote. And the idea of these stringify functions is that I can get a collection of users, stringify them all, and return a collection of strings with the stringification done. Look at the 5 lines of code here. We construct that new slice of string based on the length of users. We use our for range mechanics, right? And then we use our append function. But the real key here is that we have to call string to get the proper stringification. And we know at compile time that user has a string method, compiler can see that. I do want to take a side note for a second. Look at the function append. You know, Go has a set of built-in functions in the language. Append, new, you saw me use that. len, cap, make, delete, close. Might be missing one, copy. These are built-in functions. And what's interesting about the built-in functions, and you may never have realized this, but the built-in functions in Go are generic functions, aren't they? Look at append. Append can accept a slice of any type and a value of that same type and perform the append operation. When you really think about it, we already have generics in Go. We have the reflect package and we have the built-in types, but let's be fair. I have to be fair. The mechanics that the language team get to use to write generic functions like append, well, that's not extended to us, right? So it's easy for me to sit here and say Go already has generics. But really, we can't use the mechanics that Go gets to use to write a function like append. And we already been looking at some of the usability issues and readability issues around the empty interface and the reflect package. So there we are. But again, if you look at these 5 lines of code, we're able to use our language mechanics and syntax here to do that work. And these 5 lines of code are really the same as these 5 lines of code. The only difference is that we're working with a customer, but we know that both users and customers have this string behavior that perform the stringification. So let's go back quickly through the same exercise we went through. Is there a way to consolidate all that behavior? Yes, it is. I'm not going to spend time here. Here it is again, the empty interface. Here it is again, a type assertion. Here it is the different cases. And here it is that code. But again, this isn't a generic function because it can only work with slices of user and customer. Can we write this in a generic way today using the reflect package? There it is. It's no longer 5 lines of code. It's 13 lines of code, right? But there it is. And I promise you that if you're staring at this block of 13 lines of code and none of it makes sense to you out of the box, well, it doesn't even do that for me, and I wrote it. But let's basically walk through it really quickly, right? We use reflect value of to get a reflect value that lets us inspect the concrete data stored inside of this empty interface V. We validate that it's a slice because it could be anything. And if it's not a slice, we return nil, which kind of changes our semantics a little bit. I do have a method named len against the value when it is a slice. We can construct that slice of string. We can't use our language mechanics, our for range, but I can increment I again. I can even use on every single value that we're iterating over this method by name to validate that it has a method named string. And if it doesn't, we return nil again because I need the string behavior to be able to do the actual stringification. But if that string method does exist, I get to execute it just like we did before. We're doing it through an API, but I get to execute it. We get the data back. We then access that data and we well, this is the actual stringification. We need that to work with the append. So there it is, 13 lines of code, and I can stringify any slice of a given type that has this behavior named string. But we already talked about the readability and comprehension of this code is nowhere the same as our concrete version. So I'd like to use generics to be able to do this. without all that complexity. And there we are again. I'm going to remove this syntax very quickly for a second, and we're going to put it back in as we study this function. So once again, what do I want? I want to accept a slice of some type T. And by accepting a slice of some type T, I can use my language mechanics and get back down to the same 5 lines of code. So since we know that we need T, we might start like this. T can be anything. However, let's build this code and see what the compiler tells us. Doesn't compile. Why not? Because the compiler is telling us that on line 114, it's discovered a method called named string, and that's undefined for a value of type T. This is a constraint. This now has placed a constraint on T. T just can't be anything. It can only be of a type whose value that could be passed in with this slice exhibits that behavior. Now, this idea of behavioral constraint isn't anything new to the language, right? There is the concept of an interface that defines behavioral constraints today. Look, here's the reality, okay? I can write a function called Bill, which accepts a value of type user. This is a concrete function. It's asking data based on what is. I want a user value. But I could have written Bill to use our polymorphic, right? Or write a traditional polymorphic function by not asking for user as it is, but asking for a concrete piece of data based on what it can do. And this stringer interface, well, that's an interface already defined by the fumped package. And what it does is define a method set of one method named string that returns a string. Line 15 is a traditional polymorphic function. What it's saying is I will accept any concrete piece of data as long as it exhibits the full method set defined by this interface. It's a constraint on behavior. In this case, we're saying only if the value knows how to string. We're already using interfaces today to define behavioral constraints. So guess what? We have a behavioral constraint on string. So the current draft says, since we need to define a constraint, and in this case it can't be any, we need to tell the compiler what the constraint's going to be. In this case, the constraint is going to be this interface. And now what we're telling the compiler is T can't be anything. It can only be a type whose value can exhibit this behavior, and this interface allows us to apply the constraint. Remember, we're really using an interface here to apply a behavioral constraint for the data that for data that exhibits this behavior. But there is a slight difference here, because this is a polymorphic function asking for data based on what it can do. This, we can argue, is a polymorphic function, but it's at the compiler level. It's not here at runtime, right? From my perspective, this stringify function is no different than Bill, because at the end of the day, it's asking for data based on what it is, some concrete type T. Right? Asking for what it is, some type T. We're not asking for data necessarily based on what it can do. We're still going to be asking for data based on what it is. We're kind of still here. But the compiler has to be told that this just can't be any type, but only types whose values know how to string. And so we're going to leverage the interface, right? In a similar way we're using the interface today to define a behavioral constraint so the compiler can make sure that as it goes ahead and implements this stringify and the code calls into stringify, that value of type T that's going to be potentially passed in can exhibit this behavior. And now, with that fumped stringer interface being applied as the constraint, the code builds and compiles. Pretty cool. Okay. Because of time, I'm going to show you the last thing that I need. I'll need another 5 minutes here. And that is because this works great with behavioral constraints. However, remember, this is not a polymorph, a traditional. I'm going to say traditional because everybody's going to get upset at me, right? This is considered that parabolic, polymorphism at compile time. That's fine. I'm going to use traditional polymorphic function. This is not a traditional polymorphic function. It's not asking for data based on what it can do. It's still asking for data based on what it is. And because of that, there's another level of constraint that now has to be considered. Because there is code you're going to write where maybe we're using operators that don't apply to all types that could be T, like plus, minus, bit operations, divide. And so we need another way to apply constraints to type T, not based on a method set of behavior, but based on the potential operations that can be applied to data of those types. And so we're going to look at that and explore that now. Example 5, which will be the last thing we explore. Now, I want to go back and remove this for a second. And I want you to look again at line 16. What am I saying here? I want to take a value of some type T and a second value of some type T, add them together and return another value of type T. So again, we might think, okay, T is a generic type. We can do this. However, we can't use any because T can't be anything. Why? Because you can't do this today with a user type, can you? No. Our struct types can't be used in a plus operator. We don't have operator overloading. We can't apply that type of operation. So T just can't be anything, right? In fact, if this wasn't even a plus, if it was a minus, then this can't even be a string because you can't subtract strings. You can add them. You can't subtract them. So this is an interesting part of the draft because this is kind of technically new. We don't really have a precedent for this. This isn't a method set. This is an operator type of constraint. This is an operational constraint. But we need to be able to constrain T to be of just types that can work within the scope of this operation. Now, what the current draft is experimenting with is what you see on line 12. Because the interface right now is our way of defining constraints, instead of coming up with a new keyword, there was the idea of a contract earlier on that was doing things, all that's got removed. The idea is, can we reuse the interface to define a constraint that would satisfy the code we're writing in add? And the current idea is this: to define an interface for the constraint, but to provide that interface a list of types that would then restrict T to just that list of concrete types, knowing that these types then can operate, in this particular case, with a plus. Now, I want you to realize something, that the compiler can leverage the underlying type here. So you wouldn't have to put Bill. You don't have to do that. Since Bill has an underlying type of string, it takes on those characteristics, and the compiler would be okay. So underlying types can be identified and applied here. However, this kind of breaks the interface for our traditional polymorphic functions, because remember what I said about our traditional polymorphic functions. Our traditional polymorphic functions are based on the idea that we accept concrete data based on what they can do, not what it is, but what we can do. And our generic functions are based on what data is. And so you can't write a function like we're doing on line 16, because this has 0 sense. This isn't about writing a function in this particular case that can only work with what it is. Remember, traditional polymorphic functions are always based on what they can do. Now, the language team isn't happy about this. They're really not happy that there's a way to define an interface and then it can't be used in a traditional polymorphic function. Trust me, they're not happy about it. But they are looking for feedback and ideas and thoughts on how we can do something here without breaking interfaces for our traditional polymorphic functions and still applying the ability to put this constraint. Now, I will tell you a few of the ideas that I've seen on the mailing list. One idea was to be able to apply maybe just the operators that you want to support, and have the compiler maybe look at the fact that T has to be an operator that applies maybe to that list. That was one idea. Another idea was to just take this list and put it in here as well. But remember that one, and maybe I didn't tell you that, but one of the constraints we do have here is that you can't use two interfaces for a single identifier. So that kind of syntax doesn't even work right now anyway. You would have to leverage some composition because you can only have one interface defined per identifier. And if you had two identifiers in here, then again, you would need a constraint for all of them, whatever that other interface is. Okay, you can do that if you were applying that. And just so you know as well, while we're here, if all of them needed add only, then you could do that as well. And that would apply to all identifiers there. We do that kind of stuff today with variables, right? So the syntax makes sense. But I want you to understand that the language team isn't happy with the idea that by applying this type list of what T can be as is, it does break our ability to use the interface for our traditional polymorphic function. Now, another idea that's part of the draft is defining either these pre-declared type constraints. Here's one that's been implemented called comparable that does allow you to say that T can only be a type that works within the scope of this syntax. This would allow us to use our struct values, but you couldn't do this with slices, let's say. You can't compare two slices. Or the idea is maybe a package in the standard library that declares a bunch of these types of interfaces already that give us the base constraints that everybody would need. That's another idea. Now, one last thing I want to share with you here, so I think it's an important kind of thing to see with some flexibility, is let's focus for a second on this match function. This is the last thing we're going to do tonight here in this talk. Just focus on match for a second. What am I doing? I'm looking to write a function that can accept a slice of some type T and a value of that same type T. Range over that list of type T, and for each value in that list of type T, call some behavior named match. Passing that value of type T is the second parameter find into the match call. Now again, T is going to be a generic type, so what do we know? We know that we're going to, let's just say, start off like this. That T will be a generic type, and I'm saying anything. But we know it can't be anything. Look on line 77. We know we need a constraint because we have to make sure that T is only a value where the data of that type T can exhibit match behavior. So now we need an interface. So here we go. Let me remove this for a second. Now, remember something here. Match has to be a method that accepts a value of some type T to be determined at compile time. So look at this. When we define the matcher interface, we now say that we need a generic type T that can be anything because match has to accept a value of type T that can be anything. And now, instead of saying any, which wouldn't work anyway, we can come in here and say matcher. And now we're defining a proper constraint for T with that proper behavior that can accept a value of type T. Starting to get a little bit more complex here, right? And this is the last example I'm going to share with you. But you can see here how this idea of this type T, even through an interface here that's helping us define this constraint, may also have to be generic. Now, one of the things that I got rid of as I started this was the type list. Now, what I'm trying to show you here is that at least the draft today does support the idea that an interface may not just have a method set or may not just have a type list, but could be composed of both. So this currently is legal syntax in the draft. Now, I think we could all agree that this type constraint isn't necessary based on what we know, because I'm not doing anything like this, right? And I would be, I'm not doing anything like this, right? So I don't really need any form of a typeless constraint because I'm using behavioral constraint here If I was doing something like this, then it would be absolutely necessary. And I'll be honest with you, I struggled to find a practical example where I would have a generic function that would need both behavioral and type constraint at the same time. I really couldn't find one. Doesn't mean that one doesn't exist. I couldn't find one. But I will tell you that's something that somebody told me at a meetup several weeks ago. They saw this and they said, you know, Bill, this could be really valuable in code bases that have regulatory constraints, where you might have a function that is a really, really kind of, say, a function that you really want to kind of lock down, and you don't want anybody just being able to, say, implement an interface and be able to run code through that function. This could be a way, and maybe a regulatory way, of locking down a function to just be able to work with specific types that you know it's safe to work with, until maybe you decide that we can use a different type. And then some developer just can't come in and start executing code because they've implemented an interface that you really don't want them to implement. And then if this list changed in a code review, you'd be able to see it. I thought that was super interesting idea of being able to get kind of compiler level, maybe regulatory checks on certain code functions that you really don't want anything executing unless you know exactly that the data going through it is the right data. So I don't know. It's an interesting idea. Outside of that thought, I haven't found this. And the reality is then is, if this isn't important, if we conclude in 2, 3, 4 months from now that we don't need this type of composition, then maybe we can really find a solution and take this out of the interface, right? Maybe we can end up doing something like this, because it won't matter that we also can apply a behavioral constraint. I don't know, but this is what we're trying to experiment and understand and learn with the Go2Go tooling. And you can see here that there are still areas of this draft that need to be explored better and understood better before we lock in the syntax. Okay, so with all that being said here, I'm going to stop sharing my screen. I'm going to come back to everyone. I'm 10 minutes late. Yeah, I'm always 10 minutes late. I don't like to tell you that at the beginning because you'll be like, but that hour went by really fast, didn't it? I mean, it goes by fast for me at least. Okay, so you really did get to see, I would say 85 maybe or more % of really what's in the draft. The last 2 examples were a little more complex, but you also got to see kind of where we are in terms of things that need to be resolved. I am really excited to hear Rebecca's thoughts and comments, and since she's doing all of this other reading, it would be also interesting if she had thoughts around the last thing I showed with the type lists. So if it's okay, there's 22 people. It might be a little bit bigger group than normal. I usually give everybody an opportunity to say something and talk. I don't know if this platform lets anybody have a mic. Does this platform let somebody mic in?
I think we can do individual ones here. Let me see.
So if Rebecca's cool about talking, and then if anybody else is cool, I guess they can type in the chat or something that they'd like. They have a question or a comment. But I really love to hear Rebecca's thoughts on all of this.
Yeah, it looks like the only option I've got actually is like to invite on screen, and then that way then you could speak. I mean, obviously you don't have to have the camera on. So, Rebecca, if you're cool with that, I can try that.
Yeah, you cool with that, Rebecca? Brilliant.
Okay.
Cool.
All right.
I think we can have.
That's what I thought so. Right? And then now that the screen's not showing, that yeah. Should be, yeah. The license gives me gives 4 windows basically.
Yeah.
Right.
I'll just create a Zoom and we can go over there. Actually, that might not.
Well,
be
Bill, there was
some
talk in there that sounds like operator overloading needs to be added to the language.
Yeah. Well, I'm just going to say before Rebecca starts, don't hold your breath. Because that ain't going to happen. Don't hold your breath. There you
Can you all hear me?
Yep.
Yeah, Rebecca, we can hear you.
All right.
Yep, we can hear.
Yeah, no, it was a great talk. The first thing I think that really stuck out to me compared to the paper was the switch. In the Featherweight Go paper, they're using parentheses as the sort of syntactic element to capture type variables. And I really, there was some conversation in the chat there about sort of like parentheses versus square brackets versus angle brackets. Everybody has to bike shed the syntax, but I actually really like the square brackets. But I guess to get to your specific question about the type lists, I have to admit that, like, as I commented in the chat, like the first thing that comes to me is like, wow, they're sure going to some pretty great lengths to avoid just admitting that like addition is a function, right? Like if you even reserved operators as one of those magical things that only the language implementers are allowed to use, but still put that behind a proper interface. Like that feels like it would fit much more cleanly into the syntax in a pretty reasonable way. So I'm not really sure why they went this direction. It feels it feels not very Go-like to me, in so much as one of the things that I really like about Go is that they have done a really good job of keeping things cohesive, right? And this feels like a deviation from that, in so much as they're like, and we have this problem, let's tack this other thing on. And like, why don't we save that for JavaScript, right?
So Rebecca, let me interrupt you 1 second. If you had this conversation with Robert and Ian, you know what they would say to you? They'd say you're 100% correct. They don't like it and they're not feeling it as well. But right now they just haven't found something that was really better. So I think you're somebody. I don't know if you're active in any of the conversations, but I think it would be really nice to have your voice somewhere.
Yeah, I've been following from a distance, but not jumping in. I don't use Go day to day right now, and I think they should all ignore me anyway and listen to people that are the bread and butter user base.
Yeah. Okay.
Yeah, I think
that's good.
To add my own sort of like, I was going to say, like, to add my own sort of commentary to that. I'm also not like a Go developer day to day anymore. But one of the things that I've found that this sort of constrains the ability to, if you're a library writer, allow folks who are using your library to effectively add their type to your list of allowed types. And so like one of the things that is most interesting to me, or what I would think that you'd be able to do, is like if I'm writing a generic container or some sort of like generic library, I want to be able to constrain my container to types of a certain quality. Well, I can have my own internal interface list and type list that this container works for these sorts of types, but there's no way to allow another developer to extend that, because that list is sort of, it's compiled and you can. And that sort of reduces the usability.
And going like really far off into the weeds, I feel like the syntax that they're using there would be great in an eventual world where they had something like closed type families. And it would be a shame to waste that syntax on something like this.
Yeah, I agree with everybody here. Yeah, you'll be limited to really just application level use. You would never be able to build a third-party package, right? Because that's the beautiful thing about interfaces in Go, right? Everybody can implement that. And there we'd be locked in. So I agree with you. And that's why they're not happy. And it's a big part of what they're focusing on right now. So Rebecca, you seem, honestly, over the last 2-3 weeks for me, having the most sound and educated voice on this topic. So I know you're not working in Go day in and day out, but I just want to say to you that if you have some really good, interesting ideas, I want you to email them to me, and I'll send them to Robert and Ian directly. I mean, you don't need necessarily feel like you have to be on the public forums. They'll definitely talk to you and have that private conversation in the side channel.
Yeah, I'd be happy to do that. One other thing that I thought would be interesting to discuss, if other people are interested, is the thing that you brought up around zero values and the syntactic approach.